Okay, so let's pick up again here, and so this is 5.1. Oops. I'm actually going to pause this and go catch up. So this is where I'm meant to be. This is 5.3. So let's look at some of these very early ones. So number one, explain exactly what's meant by the statement that differentiation and integration are inverse processes. So can you do that? You can write it out in notation. So what happens if you have some function f that has some derivative, f prime, and then the relationship between the two is if you take the integral from a to b of f prime of x dx, what you get is f of b minus f of a. Another way to say the same thing is if you take the integral, or sorry, it's not exactly the same thing, but the indefinite integral version is if you take the antiderivative of f prime, you get the general antiderivative of f prime, which is f, the original function, plus some constant. So that's the relationship between the two. This is it right here. It's saying that integration, this is basically saying that integration undoes the derivative. And the other thing is true too, in the sense that if you do the derivative with respect to x of the area so far function, you just get f of x. So this is the fundamental theorem of calculus part 1. So we've got it both ways. Sorry, I don't know why it's doing that. So what's the difference between these two? Here the integral is on the left and the derivative is on the right. And here the derivative is on the left and the integral is on the right. So they sort of undo each other. I mean, there are, some asterisks and or asterisks and some footnotes. It's not totally simple, but basically the antiderivative, or sorry, the integral and the derivative are inverse in the sense that they undo each other, and the precise statements are those things that I just wrote. Okay, so let's look at some other stuff. All right. Okay, so this is the section on the definite integral, and so there are going to be a lot of questions about this g of x thing. Evaluate f is the function whose graph is shown. So where do they show this graph? Right here. So number 3 is something that you definitely need to be able to do. This was on the homework, and I have learned just through, I've taught Calculus 242 many times, and I noticed that when I do a problem like number 3 and I'm explaining to people how it works, I look out sometimes into the class, and it seems like most of the people in the classroom are just stupefied. And I think the reason is that a lot of people have really hard time understanding g of x. And so I guess maybe if we work through this exercise, maybe that's the best way to learn what g of x is. But you might also want to read through the textbook and just read the explanation of what g of x is. People really, really, really underestimate the value of reading the information in the textbook. But let's just go ahead and try to do number 3. So it says evaluate g on all these points. So let's do it. Sorry, it's being a little choppy because I'm compressing the previous video while I record this new video. So the value g, right? So what is g? Let's write it down. So g of x is the area under this curve shown in the picture from 0 up to x. And that's it, period. So it's just the area under the f curve from 0 up to whatever. So of course g of 0 is just going to be 0 because that's no area at all. From 0 to 0 has no width, so it doesn't matter what the height is. If you have no width, you don't have any area. And let's do some other values like g of 1. So again, this is sort of just square counting. It's two squares. Squares are 1 by 1, so this is 2. Let's try g of 2. So now we're going up to here, and so it's 2 plus another one is 3, and then you already had those first two, so it's 5, and g of 3 is going to be g of 2 plus these 2 more, so that's 7, and g of 6 is going to be 1, 2, 3. So it's going to be this 7 that we came up with for g of 3, and then also these things up to 7 counted negatively. So here you've got 2, 3, 4, 5. And so the difference is, this is saying 7 minus 5, which is 2. Okay. So those are just some questions about the meaning of g of x. And now we've got to do some derivatives, probably. Sketch the area. Use the fundamental theorem of calculus part 1 to find the derivative of the function. So I want you to take a look at number 7, just all of these. So sometimes, I'm a normal human being. I don't like to be criticized. But frequently I talk to students after I give an exam and they're frustrated that the exam questions are quote-unquote hard. But I feel like the student often doesn't know what hard means, and I don't decide what hard means. Mathematical culture decides what's hard and what's easy, and I'm just, the communicator of the feelings that people already have about these things. But the questions from 7 to 11, these are the very first questions of this type in the textbook. That means they are easy. That's what easy means. Easy means the first few questions in the textbook, as far as I'm concerned. So if you can't do all these, then that should set off some serious alarm bells. Okay. Alright, so let's do number 7. So we're supposed to find the derivative, and if you read the fundamental theorem of calculus part 1, it says that if g of x is what it is, the area from a to x of under the curve, then g prime is equal to f of x. So this is just what the fundamental theorem of calculus part 1, according to Stewart, says. Okay, so that's not controversial, and let's just use it. So for number 7, g prime is 1 over x cubed plus 1, that's all there is to it. It's just this particular function instead of the general f. Sorry, okay. Any of these hard at all? See, all of these are exactly the same. These are so stupid that I don't even really want to do them. Let's do one more. Let's do number 9. So g prime of x is, just rewrite the function with, I guess I should be using the variable y. WebAssign would be furious with me if I used x. So let's say y, and here is going to be y squared times sine y. Okay, so it ain't rocket science. And let's do some other things here, like where do they start to get hard? Number 11 is a little bit hard, but this explains what to do. So this is a fact that you can always reverse the order of integration if you add a negative sign. So they're just using that fact to put the x back on top. And so capital F prime is just the square root of 1 plus secant x, but then you've got to make it negative because you swapped the limits. Number 12 is exactly the same. Now for number 13 they start to get just a little bit hard. So let's look at that. So I want to I know that they're using H, I'm using G here on purpose, just to have a different letter. So wouldn't it be nice if instead of 1 over x as the top limit, it were just x. Okay. So the difference between h and g is that h is g of 1 over x. So in class, people just look at... okay, I'm sorry. I shouldn't be so honest about my feelings, but sometimes people look at me with, like, I don't know, wake up just enough to get pissed off or something, and they don't know what this means. So if you don't know what this means, pause the video and think really hard about what this means. And if after that you still don't know what it means, then look in chapter 1 of the book where it explains about compositions of functions. So if you're not getting this after a little bit of thought, and people take a little bit of thought, so it's not a bad thing if you need to think about it for a second, but if after you think about it for 30 real seconds you don't see what's going on, then you need to reread the section of the book on composition of functions. All right, and so now we find h prime, which is what we're supposed to do. And I'm just going to use the chain rule from Calculus 1. So it says that this should be g prime of 1 over x, and then I should multiply times the derivative of the inside, and the inside is x to the minus 1, so that's going to be minus x to the minus 2. And now g prime, what is g prime? Sorry. G prime is just arctan x. I'm going to write atan instead of arctan. It's just a little easier to write. So to put it all together, h prime of x is going to be atan of 1 over x times negative, let's just write that at negative 1 over x squared. And that's the final answer. If you do a bunch of these, you'll see that when there's something more complicated than x up here, you basically need to plug that expression in to the simple derivative and then multiply times its derivative. So if you had a hard time with that one, then you also need to do 14, and let's see what else they got. Yeah, so number 17 is an interesting one. It's just a combination of that rule that I just gave you combined with the trick of swapping the order of integration to get a negative sign. And I don't know, I don't think these are not, I guess they are kind of hard. So now it just says evaluate the integral. So this is asking about the fundamental theorem of calculus part 2, and this is the real bread and butter of the whole course, is being able to do these things. So eventually I would like you to be able to do these without your sheet of antiderivatives, but if you can't do them at all, then try to do them with your sheet of antiderivatives. So I'll just do a few. And we've been doing these in class a lot. Like I said before, the best thing that you can do to get ready for the test would probably be just to turn off this video and do these yourself. Because you've been watching me do these in class for a long time now, right? Do you think that if you just keep watching for a long time, then you'll eventually figure it out? If you think that, then you're wrong. It's like watching somebody play the banjo. You are never going to learn how to play the banjo by watching somebody play the banjo. You have to play the banjo. And so watching me do these problems is not going to be super helpful, but I'll try to make it as helpful as I can make it. And so what do we got after we clean all this mess up? We've got, this makes 15 over 4, and this is negative 4 minus minus 1 is negative 3. So we've got 15 over 4 minus 3, and that's good enough for me. It's good enough for you. So a lot of these are just playing around with what I just did here. So the general antiderivative of x to the n is x to the n plus 1 over n plus 1 when n, or plus c, sorry. Most important antiderivative rule, and that's always true as long as n is not equal to minus 1. And what happens when n is equal to minus 1? That's the same thing as this situation. And in that case, the answer is natural log plus c. So I guess those are, really fundamental integration rules. You learn those by doing a lot of problems. You should do all of these problems. You also need to be just super fluent in translating between different representations of the same thing. Like in number 25, 1 to 2, 3, t to the 4, dt. The key to doing a problem like this is, one, to realize that it's just asking you to rewrite this using different power notation. And the other thing is to actually be able to use the power notation. There's nothing more frustrating for you or for me than for you to miss a problem because you can't do this. All right? This is just the meaning of negative exponents. And when there are roots involved, that's just the meaning of fractional exponents. And if you can't do those things, then you don't understand the meaning of negative and fractional exponents. And that's absolutely crucial to being able to do well in this class. And it's not calculus, it's pre-calculus. And if you're not familiar with it, it's okay. I know most people actually aren't, or in my experience, a lot of people have trouble with it anyway, but it's all in chapter 1 of the book. So it's all there. And if you make an appointment with me, I can help you with it. And if you make a tutoring appointment, they can help you with it. If you read the book, you can help yourself, and you can teach yourself in a few minutes how it works. Let's try something different than that power rule. It gets kind of boring. So pi, 2 pi of cosine theta d theta. So the antiderivative of cosine is sine. And so this is sine 2 pi minus sine pi. And so sine 2 pi is 0, sine pi is 0, so this is 0. Here again, number 28, look, can you combine those exponents? They combine to make 3 halves. Do you see that? If you don't see that, you don't know enough about fractional exponents. For number 30, you've got to multiply these things out. For number 32, this is the derivative of secant. This is the derivative of hyperbolic sine. This is the derivative. Let's do number 36, actually. There's a rule that isn't used very often, or it doesn't come up too much, that it is one of the basic antiderivatives. So when you have an exponential function for some base other than e, this is a to the x, just kind of like e is its own derivative, but you've got to put natural log of a on the bottom. And you've got a plus c also. So that means the answer to number 36 is 10 to the x dx is equal to 10 to the 1 over natural log of 10 minus 10 to the 0 over natural log of 10. So what is that? That's 1 over natural log of 10 times 9. So it's 9 over the natural log of 10. All right, so what else? Number 38, this is the derivative of arctan. So the answer to this one is just arctan. So what do I mean? I'm just saying that this is one of the basic antiderivatives. So there's not really any work here to do. It's just reading off your sheet or memorization. The antiderivative of this thing is 4 times a tan. So this is 4 times a tan 1, this is 1, minus 4 times a tan 0. And if you don't remember how to evaluate inverse trig functions, then you need to know how to evaluate inverse trig functions. So the thing that makes, I think I will explain this even though it drives me absolutely crazy. Sine, cosine, and let's add tan here. And put in some rows like this, and let's do the basic angles. 0, pi over 6, pi over 4, pi over 3, and pi over 2. So you just remember the first row. Go 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. And if you don't know that, by God, you just aren't too interested in getting an A in calculus, are you? And now for the second row, 1 square root of 3 over 2, and square root of 2 over 2, and 1/2, and 0. And now the last row is sine over cosine. So 0, this becomes 1 over the square root of 3, this becomes 1, this becomes square root of 3, this becomes infinity. So that's where tangent has a vertical asymptote. So what are we trying to do here? We're trying to figure out what the values of these inverse trig functions are. So a tan of 1, what does that mean? So tangent takes an angle and gives you a number. Arctangent does the opposite. It takes the number and gives you the angle. So, stupid thing, sorry. So this is a tan of 1 is the angle pi over 4 that makes tangent spit out 1. So this is 4 times 1. And now arctangent of 0 is the angle that makes tangent be 0. So this is 4 times 0. So the answer is just 4. So these questions are the most important. You definitely have to be able to do all those. For number 40, you know, the trick is to break this up into 2 fractions. This you could do with substitution, or you could rewrite. You could rewrite e to the u plus 1. Let me just do it. Minus 1 to 1 du. It's the same thing as minus 1 to 1 e to the u times e du. Okay. So hopefully you just realized, oh, that's the trick, and now I can take e out like this. So the reason I'm disrespecting e like this is because e is just a number. Don't forget that e is just a number, so it can come out just like any other number. And this is e, and now you've got e to the 1 minus e to the minus 1. And whatever that is the answer. So it's the same thing as e squared minus 1. This is the trick here is to use arc sine. This is the derivative of arc sine. This is natural log. Multiply this out. This is the derivative of tangent. Split this up into 2 parts. Do this one case by case. I'll just tell you, I'm not going to put any like that on the exam. There will be plenty of this other type that nobody can do, I promise. That's one reason that I'm yelling into the microphone and being such a jerk. It's just, I don't know. No matter what you do, this video is not going to make any difference. You know, almost everybody's going to get every single question on the exam wrong. Sorry, I don't know why it is. It just happens. I'm trying hard, but maybe it's because I'm a pessimist. Maybe if I were an optimist, everybody would get an A. Maybe everybody will get an A. I guess that could happen. So what about these? Numbers 7 through 18. Use part 1 of the fundamental theorem of calculus to find the derivative of the function. We've already done that. That's super boring. Here's something about these that I haven't talked about too much. I guess I did talk about it a little bit, but we never really explored it. So, you know, the condition for a function to be integrable is that it's continuous over the interval of integration. And what's wrong with all of these is that that is not true. So this integration goes from -2 to 1, but this function has a discontinuity at 0. And if you graph it, like on foodplot.com or something like that, then you'll see that it's true. And that's why what you're getting here, if you think about it, it's nonsense. So they're integrating over a discontinuity. That's what's wrong with all those. So check those out and see why that's true. Interpret this as a difference of areas. No thanks. Find the derivative. Yeah, so the hint, kind of says it all here. And we've hit that pretty hard. I'm not going to do this, but we've hit that pretty hard in homework, haven't we? You've had several homework questions like number 53 here, so I think that would be a legitimate test question. These are just, you've had a homework question like number 57. Find, yeah, no thanks. What would be the, actually let's do number 58. What would be the trick here? Find the interval on which the curve is concave upward. So this curve is just y equals g of x, and you're supposed to remember from calculus 1 that being concave up is the same thing as having the second derivative being positive. And so what you would need to do is, the first derivative is just 1 over 1 plus x squared, and then, I don't know, you tell me what the second derivative is, and then you need to find the interval on which the second derivative is positive. So number 58 is pretty tough. Yeah. Okay, so I'm declaring us done with this section. I'm going to pause it and go to the next section. I'm going to unpause it here for 1 sec and point out that in this section, which I think is 5.4, there's a table of integrals. You can also print these off from the internet, of course. So this is the section on the Net Change Theorem. And what does the Net Change Theorem say? It basically says, I'm not gonna scroll up to the part of the book that describes it because I don't want to get sued for a copyright violation or get a takedown notice or something. Find my video has been deleted, but it says that the integral from a to b of f prime of x dx is equal to f of b minus f of a. Unfortunately, this is just the same. The net change theorem just is the fundamental theorem of calculus part 2. The only difference between that and what the net change theorem is trying to say is that the net change theorem is trying to tell you what this means. And what it's saying is that if you integrate a rate, then the integral of the rate is the difference in the amount. And if you never get that, it's almost like you took calculus for no reason. This is what calculus is actually used for. So can we do any problems like those? Why is it asking all these just regular integration problems? I guess they also introduced the indefinite integral. Let's just do number 11 just for the hell of it. It's right there in front of our faces. So let's do an indefinite integral. Everybody knows that that just means that there are no numbers on the stick here, and the answer is just a function, which is the antiderivative. So I said we would do number 11. So here, all of these are just the power rule, but there's some stupid trick like, does the student know how exponents work? Do you know how exponents work? So this becomes x to the minus 2 minus 2 times x to the minus 1/2. Okay. Can't do the problem if you don't know how exponents work. You guys know this is really pretentious, this classical reference to this figure from the Trojan War named Cassandra. And Cassandra could see the future, but nobody ever listened to her. And she went someplace, you know, screaming that somebody was about to be murdered, and they locked her up. Something like that, and then the person died, of course. She was a prophetess who was doomed to never be taken seriously. And sometimes I feel like that when I say, learn how exponents work. There's the answer to this question. You know, all of these have their little tricks, and maybe I'll just tell you. So this one, number 17 probably has something to do, it's probably a trick to convert back to secant squared. So you have sine squared x plus cosine squared x equals 1, and then if you divide everything by cosine, you get tan squared x plus 1 equals secant squared x. And that's kind of the snarky trick that's going on here with number 17. So number 17 is really just asking you what's the integral of secant squared alpha d alpha. They use the variable alpha. And so the answer is just tan alpha plus c, because from your chart or from your brain you know that I don't know why I said plus 1, sorry, it should be plus c. The derivative of tangent is secant squared, so this is just one of the basic antiderivative questions. Number 18 is using this trick that I said Stewart loves, and it frequently does good things. Number 18. Sine 2x is equal to 2 sine x cosine x, and you can see that if you use that trick in number 18, then the signs cancel, and it's just asking you for the antiderivative of cosine. But I'm breaking my own rule here about what's easy. I remember earlier I said that what's easy is the first few questions, so I guess 5 to 10 are easy, I would say. And then 11 and 12 are sort of medium, and I will admit that 17 and 18 here are not easy, they are hard. But as you get stronger and stronger at this stuff, what's hard changes too, you know? What's hard for you now won't be hard after you practice this a little bit more, and you've already been practicing it a little bit more. So are those still hard for you? I don't know. And now they switch back to the definite integral, and that's just because that's such an important skill. You really need to be able to do, you should just be able to bang out 21 through 30 almost as fast as you could write. Cassandra complex. And same thing for number 31 to 44. You just need to be able to do those almost as fast as you can write. Some of them have dumb tricks, but most of them don't. You know, this is just multiply n, then use the power rule, do this piece by piece. This is a question about whether or not you understand exponents. Do you understand exponents? And here you split the fraction apart. Here you do it piece by piece. This is just the derivative of secant. Split this fraction into parts and realize that 1 over cosine squared is secant squared. So what do you do here? I think if you rewrite, yeah, it's just, actually number 38 might be good. Let's do number 38. Oh, that's not the right window. Okay. Number 38. Okay, so it's a lot of writing, so I'm just going to try to simplify the expression first. And what I'm going to do is, I know that tangent is really sine over cosine. It might be that we're supposed to split that fraction up. Might not be, I don't know. But I'm going to write it like this and see if this helps at all. So this is the same thing as 1 over cosine squared theta. That's what secant really is. So what happens if I multiply, what happens if I multiply top and bottom by cosine squared? I have a feeling that that might do good things. Multiply top and bottom by cosine squared. And the reason it'll do good things is because it'll just kill that, and it'll also kill that. And so the problem becomes, what is the antiderivative of sine theta plus sine cubed theta d theta? And I could show you how to do this. We're going to learn how to do it later in the chapter. But I'm just not sure that this is what they mean, because this chapter you're not supposed to have those abilities yet. So maybe there's some easier way to do this. What happens if you break it apart? If you break it apart, you can solve. Oh, I get it. I think I get it. I'm still getting that sine cubed. Yeah, I'm sorry. So I'm just going to do it the only way I know how to do it. So obviously this thing is just negative cosine theta. So the real question is, what is the antiderivative of sine cubed theta d theta? And the trick here is to write this as sine theta times 1 minus cosine squared theta, which is the same thing as sine squared theta. And now you do u equals cosine theta, then du is, say negative du is sine theta, d theta. And then this becomes 1 minus u squared du and a negative sign, and you get 1 minus u cubed over 3 plus c. There's a negative sign. And now let's go back to cosine, so it's minus cosine theta plus, cosine cubed theta over 3 plus c. And there's this cosine here. If you want to write the final answer, it's going to be, you have to include that minus cosine. So the final answer, you have two negative cosines, so it's minus 2 cosine theta plus cosine cubed theta over 3 plus c. Okay. That's it. So that's definitely not going to be on the exam. That's pretty hard. I still think there's some secret, smart, fast way to do that that I'm just not thinking of. For number 42, I guess you just multiply out the numerator and then break it up and then use the power rule. Here you have to break it up into cases. You know, absolute value is secretly a function that's defined in terms of cases. So you need to find the point where sign becomes negative and then do the integral on that interval separately. I'm not going to do it because that's too hard for the exam. Should be able to do all of these. You know, this is just breaking up the fraction. Now this stuff is asking some things about what's the meaning of the integral, and so these are the questions in this section that are really using the net change theorem. So let's do that. Number 51 is red, so let's consider number 51. Those are usually the problems that Stuart is most proud of. So these are in some ways, you know, super easy, and in some ways not so easy. You have to be able to understand the phrase, the integral of the rate is the net change in the amount. So let's see. So here's the rate. He's even using the letter r. So here you're integrating the rate, and so here's r of t as a rate, and you can tell by the units. Right? So the units are in gallons per minute. And so what it is there's some amount function, the amount at time t, and what r of is the rate at which the amount is changing with respect to time. You know, this is just where that stupid RT thing comes from. So what they're, you know, if you want to call this A prime instead, by asking you what 0 to 120 of R of t dt is, the answer is just, you know, the amount at time 120, because that's the antiderivative, minus the amount at time 0. And so in terms of the problem, this is the amount in the whole. I know this is another thing that makes people roll their eyes in class, but nobody can roll their eyes at me now because I'm making the video. I can be as mean as I want. This is the amount of oil that's in the hole at the time when the clock says 2 minutes, right? 120 seconds is 2 minutes. This is the amount in the hole at the time when t equals 0, whenever that is. And so this is the, assuming that oil is strictly leaking from the tank, that seems to be the, you know, the intuitive thing that we're supposed to conclude from the phrasing of the problem here. So if it's strictly leaking, then this is going to be the amount of oil that's leaked out in the first 2 minutes. And that's really what they want. The answer is supposed to be a sentence in English. And so let's write it. This is the amount of oil that leaked in the first 2 minutes. And try to do it with better handwriting than me if you can. Alright, and so this is just the same thing over and over and over again. If a honeybee population starts with 100 bees, here's the starting amount, and increases at the rate n prime of t bees per week, then what does this mean? So 0, 15, n prime of t dt is going to be n of 15. And what is that? That's the minus n of 0. So this is the number of honeybees that were there initially, and this is the number of honeybees that were there at week 15. And so they're adding 100 here. This is also 100, isn't it? And so the answer, the 100s are canceling, and so the final answer is just n of 15. And what that is the amount, it's just the number of bees present at the 15th week. All right. F of x is the slope of a trail at a distance of x miles from the start of the trail. Ha ha ha, it's just the derivative. So if here's the trail, then at some point x miles from the beginning, and so here f of x is just the slope of this line, right? So in other words, f of x is the derivative of whatever curve this is. So if this is g of x, then f of x is just g prime of x. And it wants to know what happens if you integrate those things. So that's the same thing as integrating 0 to 100 of 0 to 100 of g prime of x, because that's the same thing as f of x. And this is g of 100 minus g of 0. And we'll know what this is if we just can understand what g is. And you can see from the picture that what g is the elevation of the trail. And what this is the change in elevation the net change in elevation over the first 100 distance units. And what are the distance units? Miles. What else? So can you do number 56? I guess that's a good thing to be able to do. So just read it. It's right here. If the units for x are feet and the units for a of x are pounds per foot, what are the units for dA dx? So if we think of this on top, it's a little change in a, and we know that the units for a are libs per foot, and this is a little change in x, and we know that the units for x are feet, and so this is pounds per foot squared, and that's the answer to the first part of the question. And what units does that have if you integrate this thing, so 2 to 8 ax dx. Alright, so here a of x is in libs per feet, right? And what you're doing here is you're multiplying it times something that's in, so you're multiplying it times a little bit of feet, and so this is like summing up a bunch of pounds. So the units, this equals something, and the units for this are just pounds. And that's basically because this feet and this feet cancel each other out and just leaves you with pounds. So what else have they got here? Oh, velocity, acceleration, etc., etc., etc. Number 57, the velocity function in meters per second is given for a particle moving along a line. Find the displacement, and B, the distance traveled by the particle during the given interval. So this is an important distinction between displacement and distance traveled. Let's imagine that you have something moving in a straight line. I always think of like a railroad. It's kind of hard to draw a railroad, but railroads move in a straight line because they're on a track. So just imagine, yeah, that's really ridiculously terrible. But let's imagine this is a railroad, and so he's just going forward on some track. So imagine that he goes forward, so time, start the clock, t equals 0, he's here. So he goes forward for a while, and let's say that sometime like t equals 22, he decides to turn around and go back for a few feet, and now at t equals 33, he changes his mind again, and he decides to go forward for a while, and t equals 50, he ends up right here, okay? And let's say that we had the velocity, and we integrated the velocity from 0 to 50 vt dt for this train. Now what this is going to give you is the displacement at the stop time minus the displacement at the start time, and so that's just going to give you this distance from the starting location to the stopping location, whatever that is. That's just displacement. Now, what is this crap about the total distance traveled? You can see that the total distance traveled is much greater in this case than the displacement, isn't it? Because he went forward this much, then he went backward this much, and forward this much. So the amount that he actually traveled is like much greater than just the displacement. And the way you take that into account in terms of the math is you put absolute value signs around the velocity. So the absolute value of velocity, this is the actual distance traveled. Okay, so maybe that's, you're thinking, well, I can't compute that, it's too complicated. But you can. Let's do number 59 together and work out those two things. So we'll do A, which is the velocity. What is it saying? The accelerator. Oh, I forgot where I was. 57 is where we are. So we're supposed to find A, the displacement, and B, the distance traveled. And I think it'll be helpful if I graph that for you. should really be able to graph it yourself. And it's a line, and the intercept is -5. I kind of like to put -5 right here. So here's -5. This is the t-axis. This is the v-axis, I guess. So the intercept is -5, and what makes this 0? The thing that makes this 0 is 5/3. So I'll put another little dot here, and what is 5/3? That's like just a little bit more than 1, so it's pretty steep actually. That's 5/3, and so if we were going to draw a picture of this line, then it would go, whoops, like this, through those 2 points. And this is the velocity function. I guess maybe I should call this y, actually. Forget I call that v. I didn't call that v. Can't prove it. And so in that case, this is y equals v of t. And we're looking at a certain time interval here from 0 to 3. So here's 0. 5/3 is just a little bit less than 2. And so 3 is going to be, let's say, all the way over here. And my picture is not perfect, but it captures, you know, the important features that we should be considering. So first let's do displacement. Also think about what this means. So this means that for the first almost 2 seconds the velocity was negative. That means he was going that way. Then after that the velocity is positive. He spent a little bit longer going in the negative direction than he did in the positive direction. So I'm expecting that the displacement is actually going to be negative, and that just means that they ended up to the left of where they started. But let's do it and see. So we want the integral of 3t minus 5 from 0 to 3 dt. It's very easy to find the antiderivative. This is 3 times t squared over 2 minus 5t. And we're supposed to evaluate this from 0 to 3. And that just basically means plugging in 3. So you've got 27 over 2 minus 15. And like I said, this is just a negative number. What it means is the displacement. And so if I can sort of sketch for you what happened to the particle, initially the particle was moving to the left because initially the velocity was negative. And then at a certain point in time, namely t equals 5/3 seconds, so here's t equals 0, it turned around and started moving forward again, but it was going at a constant rate the whole time, and it only had like a little bit more than 1 second to go back in the positive direction, and so it ended up here at t equals 3. Now the displacement is going to be the difference between the starting and the stopping place, so it's going to be that distance. You can tell that's a lot less than how far it actually went, right? Now let's try to find the total distance. That's what we're supposed to find for b. So the way we do that is first we integrate from 0 to 5/3, and we know that it was negative that whole time, so I'm going to multiply the function by -1 on that part. And this is going to force it to be positive. So that's going to be, you can figure it out for yourself. This is just going to be 3 times 25 over 9 over 2 minus 25 over 3. So I don't care. But that's not the whole story. So that just counted the part that used to be counted as motion in the undesirable direction, motion to the left. By forcing it to be positive by reversing the order of subtraction, I've made it count as movement in the right direction. And so I'm counting all movement that occurs as movement rightward. And I still have to take into account what happened between here and here. And I need to use the original because this is what makes that positive. And this is just 3t squared over 2 minus 5t between 3 and 5/3. Now that's going to be some number, and if you sum these two numbers, then what you get is the total distance traveled. I think you spell traveled with just one L. Okay, so that's it. And what else have they got here? Oh my god, linear density. You know what, I'm feeling kind of tired. You should be able to do this linear density problem, but I'm too tired to do it right now. I'm going to skip it and pause the video for a while.